What is going on, guys? My name is Amos and I'm back again with another video. So in this video we want to see how we can decompose this rational fraction, of course in R, right? We want to see how we can decompose this rational fraction. Now this is our polynomial A, and then now this is going to be our polynomial B, and then we can clearly see that these two polynomials are irreducible. This rational fraction is irreducible, right? It's going to be irreducible, meaning A and B do not have any common divisors. Now the first thing that we want to do is to check the degree of the numerator and the denominator, right? We're going to check the degree of the numerator and the degree of the denominator. Now here we see that the degree of the numerator is 1 and the degree of the denominator is 2. Now here we see that the degree of A is strictly less than the degree of B. Now this is what we observe, and so we can apply the decomposition technique that we are supposed to apply. Now here we're going to look at our denominator, which is going to be this quadratic expression here, x squared minus 3x plus 2. Now we're going to see if this denominator is going to be factorizable. Now to see if a quadratic expression is going to be factorizable or not, we have to calculate its discriminant. Now the discriminant of a quadratic expression is going to be given by the formula b squared minus 4ac. Now if we look at our quadratic expression, we have that a is equal to 1 and b is equal to minus 3 and then c is going to be equal to 2. Now we replace in the formula, we get that the discriminant is going to be minus 3 squared and then minus 4, and then we're going to have 1, and then we're going to have 2 here. Now here we're going to have minus 3 to the power 2 is going to be 9, and then minus 4 multiplied by 1 is minus 4, minus 4 multiplied by 2 is going to be minus 8. Now this is going to be equal to 1, and then 1 is strictly greater than 0, and so quadratic expression is going to be factorizable. Now if you want this quadratic expression, x squared minus 3x plus 2 is going to be factorizable, and then it is going to be written as a product of two linear factors. Now we're going to have x minus 1 here. We're also going to have x minus 2, and so we see how best we can write our rational fraction. So now we're going to create a new page. Then we're going to have f1 is now going to be equal to x divided by x minus 1, and we'll have x minus 2. Now here, this is a linear factor. Now this is going to be a linear factor, and the second one also is another linear factor. So basically we have our denominator expressed as a product of two linear factors. Now the decomposition here is going to be very simple. So here f1 is going to be written in the following form. So we're going to have a scalar that we're going to call alpha here, and then it is going to be divided by the first linear factor. So here we're going to have x minus 1 and then plus, and then here we're going to have another scalar which is going to be beta and then divided by the second linear factor. So we have to find the values of alpha and beta, all right, that are going to give us this decomposition, right? So here for f1 here we're going to substitute our rational fraction. So here we're going to have x, and then here we're going to have divided by x minus 1, and then here we're going to have x minus 2. Now the first thing that we want to do here is if we want to compute the value of alpha, we have to multiply by the denominator of alpha, which is x, which is the linear factor x minus 1. So that is what we do here. So we're supposed to find the value of alpha. So here we're going to multiply by the denominator of alpha, which is the linear factor x minus 1. So here we're going to have x minus 1 multiplied by everything. So if we multiply x minus 1 throughout, we're going to have x divided by x minus 2. Now this is going to be equal to alpha plus beta multiplied by x minus 1 divided by x minus 2. Now this is what we have, right? So now what we're going to do to compute alpha is to replace, we're going to choose a value of x. We're going to take x equal to a certain value such that this part goes to 0, such that this part is going to be equal to 0. So what value of x is that going to be? Now if we take 2 for example, the numerator is going to be 0, and we have 0 over a numerator that is going to be non-zero, and that is going to be a problem. So we want to try to avoid that situation. So here the possible value of x that we are going to take such that the second term is equal to 0 is going to be x is equal to 1. So we substitute x is equal to 1 here. We're going to find that alpha is going to be equal to, so here we're going to have alpha is going to be equal to 1 divided by 1 minus 2, So alpha is going to be equal to 1 minus 2 is going to be minus 1. So alpha is going to be equal to minus 1. Now we've computed the value of alpha, which is going to be minus 1. We now try to compute the value of beta, right? To compute beta, we have to multiply by the... Now we're going to rewrite this expression on another page. So here we're going to say, now our f1 is going to be x, and then here we have x divided by x minus 1, and then we have x minus 2. Now this is equal to, now we're going to have alpha. So basically here what we've done is we've gotten this expression. What we've done here is that we've gotten this expression here, this expression. Now I'm going to call this expression star. So we've gotten this expression star. Now we've rewritten the expression star, and now we want to compute the value of beta. So that is what we've done here, right? In case you guys are lost. So here we have x divided by x minus 1 multiplied by x minus 2 is alpha. Here we have x minus 1, and then here we have beta divided by x minus 2. Now what we do here is that we're going to multiply by the linear factor, that is the denominator here in this rational fraction, in this fraction b divided by beta divided by x minus 2. So here we're going to multiply by the linear factor x minus 2 throughout. So when we multiply here, we're going to have x divided by x minus 1 is going to be equal to, now here we're going to have alpha multiplied by x minus 2 divided by x minus 1, right? And then here we're going to have plus beta. Now we choose a simple value of x such that the first term, this term here, is going to be equal to 0. So here we cannot choose x is equal to 1 because the numerator is going to be 0, and then we're going to have the denominator is going to be 0, and then we're going to have a numerator that is non-zero. So that is going to be a problem. Division by 0 is going to be our problem there. So here we're going to choose x is going to be equal to 2, because if I substitute 2 here, the numerator is going to be 0 by making the entire fraction 0. So here we're going to have that beta is going to be equal to, so here x is 2. So here we should have 2 divided by 2 minus 1. Now this is going to be equal to 2 minus 1 is 1, so beta is going to be equal to 2. And so we can rewrite our rational fraction, which is f1. It is going to be equal to, now alpha is minus 1 divided by x minus 1, and then plus 2 divided by x minus 2, like so. So this is how we can decompose our rational fraction. Now this is the first method. There's also a second method that you can apply. Now what is that second method? Let's look at the second method that you can apply here, right? So now this is our answer. So we're going to keep this as our answer, and then after applying the second method, we're going to verify whether we get the same thing or not. So this is going to be our answer, and then we're going to call this answer star star, like so. Now we're going to create a new page and then look at the second method that we can apply here. So we basically have f1 is going to be equal to x divided by x minus 1 and x minus 2. Now if you recall what I said in the very first video, now the roots of the denominator are going to be known as poles. So here we basically have two simple poles, right? We have two simple poles. Now the first pole here is going, so I'm going to say pole 1 here. Pole 1 is going to be equal to 1. Now the second pole, which is going to be pole 2, like so, is going to be equal to 2, because we know that if we substitute 1 here, the polynomial b, which is the denominator, is going to be 0. It is going to be 0. So 1 is going to be a root of the polynomial b. So we basically have two poles here. So we have pole 1, which is 1, and pole 2, which is going to be 2. Now what we're going to do is to take the derivative of we take the derivative of b. Now we might want to rewrite our denominator in the following way: x squared minus 3x plus 2. That is, we expand. Instead of it being represented as a product of two linear factors, we're just going to give the quadratic expression that is going to be there. So here we basically have x divided by x squared minus 3x plus 2. Now the first thing that we want to do is to find the derivative of the polynomial b, which is our denominator. So now b prime of x is going to be equal to 2x minus 3. Now that is our first derivative, and then we want to look at this fraction. So we want to look at this fraction. So generally what we have to do is that here we're going to have a of alpha divided by b prime of alpha. Now, where alpha is going to be a pole, a simple pole of our denominator. So this is what we want to compute. And then here we take, so here what we're going to say is, we have to rewrite this in another way. So we're going to say it is a of x divided by b prime of x, like so. And instead of having pole 1 here, I'm going to say that this is going to be alpha 1. And then instead of having pole 2 here, just for simplicity, now this is going to be alpha 2. Now here we're going to take x is equal to alpha 2. And then we also need to compute the quantity ax divided by b prime of x. And then here we're going to take x is going to be equal to alpha 2. So here this is not alpha 2, but this is going to be alpha 1. So this is what we are supposed, this is the calculation we're supposed to perform. Now, our rational fraction is therefore going to be written in, in this, it is going to be written, we're going to find, the decomposition of our rational fraction into two, other fractions, right? So let's compute this. Let's compute this. So the b prime of x is equal to 2x minus 3. So let's see what we get. Now here we have x. Now our a is x, and then our b prime of x is going to be 2x minus 3. Now here what we're going to do is that we're going to substitute x is equal to 1. Now 1 is the first pole of our quadratic expression. Now if we substitute 1 here, what do we get? So here we're going to get, if we substitute 1, now this is going to give us 1 divided by 2 multiplied by 1 minus 3, like so. Now this is going to be equal to 1 divided by minus 1. Now the first scalar that we're supposed to find, the first scalar, we're going to call it beta 1. Now the first scalar is going to be beta 1, which is going to be minus 1. Right, and then for us to find the second scalar, which is going to be beta 2, we have to say it is going to be 2x divided by 2x. It is going to be x divided by 2x minus 3. Now here we're going to take x is equal to the second pole of our quadratic expression. The second pole was 2. Now this is going to give us 1 divided by 2 multiplied by 2 minus 3. Right, so this is what we're going to get. Now 2 multiplied by here we're supposed to have 2, not 1. Sorry, that was a mistake. So this is supposed to be 2. Remember, x is 2 here, so we substitute 2. So here we're going to get 2 divided by 1. Now here our beta 2 is going to be equal to 2, and so we get that our rational fraction is going to be decomposed in the following way. So we have x divided by x minus 1, and then we have x minus 2. Now the pole that was associated to this linear factor is 1, and then the pole that was associated to this linear factor is 2. And so here we must have a beta 1 divided by x minus 1, and then plus beta 2 divided by x minus 2. Now our beta 1 is minus 1, and then this is divided by x minus 1, plus our beta 2 is going to be 2 divided by x minus 2. Now the second method is known as the derivative method. Now this is going to be very, very useful, especially when the denominator is given as as an expression, such as a quadratic expression or a polynomial, right? Where we have x to the power 3, and then we cannot factorize. So this is going to be very useful in that case, where you basically identify the poles of the denominator and then try to take the derivative of the denominator. And then what you have to compute is a of x divided by b prime of x, and then you take x is equal to the first pole. Now to find the other quantity, you take x is going to be equal to the second pole. Now here the poles that we're talking about are simple poles, meaning the linear factor where the pole is going to come from is going to, the highest power of that linear factor is going to be 1, right? So we're talking about simple poles. Now when we get to double poles and things like that, now we're going to look at the method that you guys are supposed to apply for you to decompose your rational fraction into into simple fractions like this. So for example, here if you're taking the integral, what you have to do is that the integral of this rational fraction is going to be equal to the sum of the integrals of these simple functions. Now here, beta 1 is going to be a constant and beta 2 is going to be a constant. And then those of you who have done integration know what this is going to mean when we're talking about integration and all that. So you're going to basically have natural log of x minus 1, natural log of x minus 1 as your primitive, right? So I'll see you guys in the next video.